Hey guys, today we're going to start section 4.6. The title of this section is Graphing with Calculus and Calculators, but I changed the title on my video anyway to Graphing with Calculators, Computers, and Calculus. You might notice we skipped section 4.5. The title of that was Summary of Curve Sketching. The reason I skipped that is because curve sketching is not really as important of a skill as it used to be. When I first took calculus back in the 90s, curve sketching, it wasn't really easy to graph a curve. What I mean by that is we didn't have graphing. We didn't have a lot of graphing software available. I did have a graphing calculator back then, but they weren't common. They weren't things that everybody had, and there certainly wasn't Desmos that everybody can use. So it was important to be able to go through and figure out all the different aspects of a graph and then draw that graph. Well, today it's more important to be able to graph it on a computer and then be able to go in and find all of the relevant information. So what I want to do is just a few examples where we use a computer to give us a graph, and then we'll use calculus to find the exact values, and then we'll also, let's see, I've got an example at the end where we're going to do some approximations using Desmos. So let's look at this one. I've got the graph of this fourth degree polynomial here, and it says find the exact values of its intervals of concavity. Now before we do the exact values, let's look at it. Let's see, it's concave up here because it's shaped like a cup, and then over here it's concave up again, and so it looks like somewhere in here is where it's concave down. So we should expect to find an inflection point here and here somewhere. And just from looking at the graph, we can kind of eyeball them, but let's find the exact values of those. So let's see. To figure out the concavity, we need the second derivative. So f prime here is going to be 4x cubed minus 3x squared minus 6x plus 1. And f double prime is going to be 12x squared minus 6x minus 6. So let's take that and set it equal to 0, and we'll find those hypercritical numbers. 12x squared minus 6x minus 6 equals 0. Divide both sides by 6, you get 2x squared minus x minus 1. And this should factor into, let's see, I believe it'll factor into that. If we make this minus and this plus, that makes my outside be minus 2x, inside is plus x, so that gives us what we need there, and our last gives us negative 1. So yeah, that'll do it. So we get here our x equals negative 1/2 and x equals 1. So those are the x coordinates of my hypercritical numbers. And honestly, if I come over here and I graph them, or if I mark them on the graph, let's see, x equals negative 1/2. So that's going to be here-ish. Let me change to a, no, that's a good color. So if I come down to here, it looks like this is my one inflection point. And the other inflection point happens here at x equals 1. Now I could go in and work out the y coordinates. Actually, the y coordinates look like negative 1 and negative 2. But it was asking for the intervals of concavity. Now, I could, previously when we did intervals of concavity, I would split up the real number line and then test my values there. But since we've got the graph here, we don't need it. We don't need to do that. We can look at the graph and say, it's concave up here and here, and it's concave down in the middle. So let's see, so concave up, that's going to be on minus infinity to negative 1/2, and from 1 to infinity is concave down in between, from negative 1/2 to 1. And I've got the inflection points labeled there, and that's really all we need to do for this problem. I want to do a couple more examples, but I think I'm going to put them in different separate videos. So we'll stop here.